Hi, my name is René Williams. I'm an assistant professor at the Molecular Photonics group at the University of Amsterdam. And today we will discuss photoinduced electron transfer, and we will talk about the semi-classical Marcus theory. Now, I have to warn you, we will start off simple, but then after making sure that you are secured, then we will bungee jump into the canyon of the Marcus inverted region, and we will go into an area that is also uncharted territory for me. However, we will resurface, and then in the next lecture, we will make a slow walking tour into that same canyon. So my first question to you is, does anybody know who this is? Does anybody know this guy? Well, you may not know him, but it is the third Nobel Prize winner in chemistry, Arrhenius. It is Arrhenius. My second question to you is, please stop this video and write down the Arrhenius equation, or what you know of it. What you know of the Arrhenius equation. Okay, welcome back. This is the Arrhenius equation, and it describes the rate as a function of temperature, the activation energy. Here, the activation energy is here, and it also contains the pre-exponential factor. Now, the pre-exponential factor basically is the maximum rate that the reaction can attain, because if the activation energy is 0, then this becomes 1, and so then you have the maximum rate. And this rate is roughly 10 to the power 12, 10 to the power 13 per second. If you look at transition state theory, then it is kBt over h. So that gives the order. So if we plot the natural logarithm of the rate versus 1 over the temperature, then the slope gives us the activation energy. And well, basically, basically the Arrhenius equation basically contains two parameters, the pre-exponential factor and the activation energy. So my third question is, does anybody know who this is? Well, this is Rudolf Marcus. He got the Nobel Prize about 90 years later, and basically for developing the theory of electron transfer. And well, this represents Marcus theory. So basically Marcus theory is based on two intersecting quadratic functions, and they represent the reactant and the product. And the y-axis is energy, the x-axis is nuclear and solvent coordinates. You can also call it a reaction coordinate. So the Marcus equation, basically, it contains three important parameters: the delta G, so the exergonicity, the driving force, the lambda, the reorganization energy, and the phi. Now the phi, that is the electronic coupling. It tells you something about the overlap of the electronic wave functions of the electron donor and the electron acceptor, the D and the A. and it is a measure for the interaction between the two states. So here, these two states, they interact, they mix, and this is the strength with which they mix, and that is related to the electronic coupling of the wave functions of the donor and the acceptor. The delta G, that is the driving force of the reaction. So how exergonic is it? And what is the energy difference between the donor and acceptor in their neutral state and the state, the charge transfer state, in which we have formed the radical cation of the donor and the radical anion of the acceptor. So this should be lower. So mathematically, the delta G is just the delta Y value. So the Y difference between these two minima. The reorganization energy, that is a very important part, a very important contribution from Marcus, and it contains an inner sphere and an outer sphere. So we have an internal or inner sphere reorganization energy, and we have an outer sphere, a solvent reorganization energy. Basically, the difference in nuclear coordinates, so the delta X of the two minima, if we square this delta X, then we get the reorganization energy. So it is the energy that is associated to converting one state into the nuclear coordinates of the other. So if we go from here, we go all the way up, this energy that is related to the change in nuclear coordinates. So that is the reorganization energy. So if we look at the pre-exponential factor of this equation, this is the rate of the electron transfer, then it contains this lambda and this electronic coupling. For the rest, it's just basically just constants. So we find the Boltzmann, the temperature, pi, and h, Planck's constant, they're all normal. And in the exponential term, there we find the delta G and the lambda. So this is what we call the classical Marcus expression, and it relates to intersecting quadratic functions. And very important, the reorganization energy. So the inner sphere and outer sphere reorganization energy, the reorganization energy that is related to changes in the molecule and changes in the solvent. So if we compare the Arrhenius equation to the one of Marcus, then we see that they're actually rather similar. So the pre-exponential factor, the A here, that is specified into different quantities like the electronic coupling and the reorganization energy. If we look at the exponential term, then we see that the delta G, the activation energy, that is expressed as in terms of driving force and reorganization energy, and it is based on quadratic functions at the crossing point of two quadratic functions. So basically, it is related to the delta Y and the square of the delta X. Now, it has turned out that the classical Marcus equation, that it strongly underestimates the rate of electron transfer in the inverted region. So in practice, the observed rates in the inverted region, they are much higher than predicted by this classical equation. So the classical barrier is much too high. How to solve this? Well, we have to take into account nuclear tunneling, also called the overlap of vibrational wave functions, vibrational mixing, or the Franck-Condon weight density of states. So we have to take one step further. We go from the classical Marcus to the semi-classical Marcus equation. It's also called the Marcus-Jortner-Lewitsch equation. And then we see that the pre-exponential factor, that is actually almost the same, but the classical contains the total lambda, the semiclassical contains only the solvent reorganization, so the outer sphere reorganization energy, and not the total lambda. Now, the second part of the equation, that has changed because it is now containing a summation of functions. And in the part of the activation energy, in this part, there we see that a vibration is now playing a role. And this vibration, it is basically a vibration of the molecule that mediates the electron transfer. It's also present here in this S function. So that is what we call the Wang-Rice factor, which is the ratio of the internal reorganization energy and the energy of this vibration. So this here, actually, it is like a scaling factor. It reduces the intensity of the summation as m increases. Now, as you may know, the first proof of the Marcus inverted region that came from Kloss and Miller. So they studied a charge shift reaction, and they changed the nature of the acceptor and thereby changed the driving force. So this is the driving force, the delta G, gives free energy change. So they changed that by changing the electron acceptor strength. So in the semi-classical approach, you see that so this is the classical approach where we have a classical barrier that we really have to overcome. Now in the semi-classical approach, this implies the overlap of vibrational wave functions. So that is this Franck-Condon factor. So not only the electronic parts play a role, but also the vibrational parts. So the overlap of vibrational wave functions in the inverted region, it increases and it becomes more important, and that makes the rates faster. And we will get back to this. So, as you may know, the classical Marcus expression has made it into the textbook like Physical Chemistry of Atkins. This picture is from there, and there it shows the classical way, this classical curve, the bell-shaped Marcus curve, where the rate versus the driving force is given. Now, we have seen before in previous lectures that the Born-Oppenheimer approximation, which tells us that we can separate the electronic part and the nuclear part, that this approximation is not always valid in photochemistry, like for instance in the forbidden transitions of pyrene. Electronic transitions and vibrational transitions, they can influence each other, they can mix, and they can work together in what we call vibronic coupling. So this concept, this is expressed in Fermi's golden rule. So that's actually the same Fermi as from the Fermi levels. And this golden rule, it tells us that the rate of a reaction can be related to the electronic coupling and this overlap of vibrational wave functions. So Fermi's golden rule tells us that the rate is the product of an electronic part, the overlap of electronic wave functions, and a vibrational part, the overlap of vibrational wave functions. This last part is more important in the Marcus inverted region. So this picture here, This is basically the best way that we can represent this overlap of vibrational wave functions. So here we see the reactant state, the product state. We see all the vibrational wave functions that are drawn in. And this here in black, this is the overlap of the vibrational wave functions. So that is the overlap. Now, mathematically, it is the second part of this equation. So the Franck-Condon term is the summation of these exponential functions with this factor, this normalization or this scaling factor in front. Yeah. So this is the same equation that I showed you before. Basically, it's the same. And this shows you this Franck-Condon factor in the normal region. So here we see again this picture that I showed you before. So here we have the, okay, this is the classical Marcus equation. And we see that the rate drops very fast. Now in the semiclassical Marcus equation, the rate sort of goes down more slowly, and it is due to overlap of vibrational wave functions. So this is in the normal region. This is the overlap of vibrational wave functions in the inverted region. And hopefully you see that here, the black area is basically larger. And so this overlap enhances the rate in the Marcus semiclassical expression. So we can encounter the semiclassical Marcus equation in various ways. This is basically the same what we saw before. It contains it contains 5 parameters: this delta G, the solvent reorganization, internal reorganization, electronic coupling, and this particular vibration. So this is a vibration that is related to the vibronic coupling. We can also encounter basically the same expression. We can encounter it in other places, like in an ADF tutorial. So ADF, this is like state-of-the-art computational program. It uses, well, something that is basically the same as the semiclassical Marcus equation that I just showed you. The only difference is that in this case, this is not the electronic coupling, but it's actually the matrix element for spin-orbit coupling. So they apply it to, in a study related to terminally activated delayed fluorescence. So the triplets and the singlet play a role, but this part is basically, mathematically, it's the same as the semiclassical Marcus equation. So also the Wang-Rice factor, you can calculate it with ADF, so that makes it very approachable. Okay, now we begin exploring the depth of the canyon. So here we see a 3-dimensional representation of the classical Marcus expression. This here at the z-axis, the z-axis, that is the rate as a function of the driving force, the delta G at the x-axis, and on the y-axis, we have the solvent reorganization energy. So that is the x, the y, and the z. So you see that if we stay on the ridge of this mountain, then we stay in the Marcus optimal region. So there we have the highest rate that can be attained for these specific conditions. And you also see that the rates that you can attain are actually highest at small delta G's and small reorganization energy. Now that is part, it is within the Marcus theory, and people have observed that also. Now, actually, this here, it's not the classical Marcus expression, but it is the semi-classical Marcus expression, but then from m is 1 to 1. So just with one exponential term. So, but basically the classical Marcus expression looks the same. But now we can do a little trick. I hope we can. So we can see what happens if we increase m from 1 going to 2 and up. And we go, and now it's up to 2. We go up to 3, all the way up to m is 15. And if you go beyond 15, then actually the influence becomes smaller and smaller. So you see that the summation factor keeps on adding in the inverted region. This is how the semi-classical expression handles the overlap of the vibrational wave functions. So that is the way that the rate is increased in the Marcus inverted region. But you see that the extra additions, they become smaller and smaller as m here, as this factor in the summation, as it increases. And so you don't have to go very far. Now, the peaks in the background, they are, well, let's call them intriguing. And if we approach these peaks, we can just approach them. So now we see now 1, 2, 3, 4, 5, 6, 7, 8, 9. You see that the contribution becomes smaller and smaller. So now we approach these peaks in the back, and here you see them. So if we approach these peaks, we actually see that oscillation starts to occur in the bell-shaped Marcus curve. Now I have found 3 old papers that describe these effects, but I would like to know more about this. Are these the limits of the semi-classical Marcus expression, or can we actually observe these effects experimentally, or maybe have they already been observed? So we have made a trip from Arrhenius to Marcus, then onto the Franck Condon factors, all the way, well, to the depth of the canyon, where, well, experimental proof, I think, is lacking for these kind of oscillations. I hope that you have survived this bungee jump and that your harness is still fixed. So we have visualized complex mathematical approaches made by Nobel Prize winners to show how the rate of a simple reaction, the movement of an electron, how this rate is influenced by many factors. Thank you.